Welcome to lecture 23. So in the last class we have seen the importance of the step response and impulse response. I mean to say, why should we use the impulse response to analyze the circuit? Now based on it, let us solve a couple of examples on how to find out the impulse response or step response. So suppose I have simple RC circuit like this. Okay, and to this I have given delta as an input to it, R and C. So I want to find out what is the impulse response of it, or what is the delta response. And again, given that suppose all my initial condition is 0 here, which means that your VC of 0 positive also. Okay, so let us write the differential equation from it, and we have to solve it, say, for I. So your delta of t will be IR plus 1 over C integral 0 negative to t v of tau not v of tau will come here, I of tau d tau. Okay, and now I will use you can solve using the differential approach, but here I am using the Laplace to get it the answer quickly. So we know the Laplace transform delta is 1, which is R I of s. The Laplace transform is this, and 1 over Cs into I of s, and this I can write in terms of I of s as this is C into S. Okay, so RCS plus 1 CS will be numerator, and denominator it will be RCS plus 1, and I want the coefficient of S is to be 1, so that I can write as C will get it cancelled, so it will be 1 over R. It is 1 over R, and it will be S over S plus 1 over RC. Okay, and this I can I use the inverse pair? No, I cannot use, because the order of numerator is equal to order of denominator here. So what I have to do, I have to do the quotient, that is I have to divide numerator and denominator, and I have to write in terms of quotient plus remainder upon divisor, right? So it is 1 S plus 1 over RC, so it will be minus RC, so it is 1 by R, quotient is 1, minus remainder is 1 by RC into divisor is 1 plus S plus 1 over C, S plus 1 by RC. Okay, and now I will take the inverse Laplace, which is standard pair. It is the inverse of 1 is delta t minus 1 over RC into inverse of S plus A is e raised to minus AT. So it is minus 1 by RC into t, it is 1 by RC. It's not, it is minus 1 over RC into t into, remember, it is U of t. Okay. So now if I would like to plot it, I can see that this I of t consists of two terms. One is your delta function, second is your exponential decreasing function, right? So if I would like to plot it, how the plot looks like. So suppose this is the plot for I of t. So first it consists of delta function, which is 1 over R, the strength is 1 over R, and this will be minus 1 over RC, so it will be exponentially decreasing this way. Okay, and the addition of it will be my impulse response. Okay, so this way you can find it out. Now next, suppose I'll ask you find out the step response. So what you can do, instead of delta function, you can apply the unit step function here, that is U of t, and already such kind of thing we have solved it. So that two ways you can do. You can write the differential equation, you can find out the Laplace transform, and you can find out inverse Laplace transform, that way which we have done. Or we know that the integral of delta is unit step, so I know the impulse response. If you find out the integral of impulse response, that is as good as your step response, right? So what I will do, if I would like to find out the step response, I will integrate the delta response or impulse response, say from minus 0 negative to t. Okay, So if we'll integrate this, it will be what? It is 1 by r integral delta t, so it will be u of t, right? And the integral of minus 1 over rc. So this strength is not minus 1 over r, it is minus 1 over r square c, because 1 by r is multiplying with this. Okay, then what next? The integral of second term will be 1 over rc, and r square is there, so it will be plus rc over r square by c, and higher limit and lower limit, so it will be e raised to minus t upon rc, and minus same rc over r square c into 1, which is u of t. Okay, so it is 1 over r u of t plus 1 over r e raised to minus t upon r c into u of t, and minus 1 by r u of t. So this term will vanish. So your step response will be, as per our expectation, it is 1 by r e raised to minus t over r c into u of t. So that way you can find out the step response also. Now next example, parallel RC circuit. So in that, say this is my switch, and to that current source is connected, and there is a resistor attached with capacitor here. Okay, so this is say my I1, and switch is closed at t is equal to 0, and say initial condition is 0, which is Vc of 0 plus, and I have Vc which is equal to Vc of 0 plus. Now I would like to solve for V1 of t. So V1 of t or V of t, because there is no V1, V2, etc. So okay, so how can we do? That is V of s, I can calculate using RCS upon 1 plus RCS into the Laplace of I1, which is I1 by s. So you can write as RCS upon 1 plus RCS into the Laplace transform of the excitation, which is I1 over s. Okay, and I want to make the coefficient of s is equal to 1, so RC I will take it common, so RC will vanish here. Okay, and I1 by c will come. Okay. So this will be, if you solve, it will be I1 upon c, and it is 1 over s into s plus 1 by rc, and then I will use the partial fraction here, so I1 over c, a upon s plus b upon s plus 1 by rc, and you can find out the values of a and b. So a is rc, b is minus rc, by the way we have seen in finding out the inverse Laplace transform, right? So this is v of s will be I1 into rc upon c, it is 1 by s minus 1 upon s plus 1 by rc, and which is I1 r into 1 minus a raised to minus t by rc into u of t. Okay, that is my v of t, right? And we can verify it by physical inspection. So what will be v of 0 at t is equal to 0? When switch is closed, current source is connected to this parallel RC, so C has been initially relaxed, right? So what will happen at t is equal to 0? So the voltage will be 0, okay, because the capacitor, initial relaxed capacitor, has been act as a short circuit, and if I will connect this current source for a long time across it, what will happen? Your capacitor has been fully charged, so no current will flow through it. It means that your voltage across it will be I1 into R. That we can achieve from here. Okay. Now to this, instead of unit step, this is for unit step, right? Now instead of unit step, if I would like to calculate delta, so you can differentiate it you will get the delta response or impulse response. Okay, so for finding out the impulse response, what you just differentiate the step response. Okay, and if you differentiate the step response, you will get the impulse response. So we can find out the impulse response of it. That is by the use of differentiate by differentiating this step response, you will get the impulse response. That is what I wanted to take. Okay, this is easy. Then again, now suppose to the same circuit, parallel RC circuit, now I'll apply the excitation as pulse like this. Okay, whose magnitude is 1, say period is 0 to t. Fine. And this is my excitation now. Say magnitude is I1, for example, here. So this, how can you approximate? So that can be approximated by the subtraction of two unit step signals. One is like this, whose magnitude is I1 from 0 to t, and next is again the unit step response, which is I1 from t onwards. Okay, and if I'll subtract this and this, I'll get it this signal. So, and already we have seen, say this is my I of t excitation. So already we have seen what is the response. What is the response for this? We have calculated it is I1 into R 1 minus e raised to minus t upon RC into u of t. Now I would like to calculate what is the response of it. So in this case, what we have done, we have just shifted the unit step function by an amount of capital T towards right. So what will happen, your voltage will also that is output will also be shifted by the same amount because of its time invariance property. So it will be T minus capital T over RC, and this will be because of the causality, it will come as U of T minus capital T. Here note that I cannot write U of T. Okay, because if I write U of T, what does it mean? It is the response we are computing at t is equal to 0. But what is the input or what is the excitation? Excitation is the input. Excitation is the step function which has been applied after shifting this u of t by capital T towards right, or the unit step signal will start from capital T. But if I write u of t, what is happening, that output is happening at t is equal to 0, so which is anticipatory, right? And it will not satisfy the causality. That's why the thing is to be u of t minus capital T. Okay, and now I will write total v of t, which is this is the I1 u of t minus I1 u of t minus capital T. So I can use the linearity property, and same I can write for its responses also. So total response v of t will be equal to the output due to I1 of t, so which is I1 R 1 minus e raised to minus t upon RC into u of t minus I1 R 1 minus e raised to minus t upon minus capital T over RC into u of t minus capital T. Okay, and now let us plot it. So if I would like to plot, how will be my total V? This is my total V. So first it will be I1R. So what will be, it is exponentially increasing this way. Okay, and the second term is T. It will start from negative way. So it is exponentially increasing negative direction like this with the same magnitude, that is I1R with negative sign. Okay. So if I subtract this and this, what will happen? The resultant output will be something like this. Okay, and from here it will be smoothly discharged. And what is the input? Input is something like this. Okay, so what I am observing, if input was the excitation applied to the circuit is like this, it was 0 at t is equal to 0, current source or energy source has been connected to parallel RC. So at that time what will happen? Capacitor will charged and voltage across it will be linearly, will exponentially increasing, and it has been charged fully. And after suppose it has been charged fully, and after that I have removed my energy source. So what happened? The charge capacitor is trying to discharge it in exponential manner, and this is the reason it is coming down this way. Okay, fine. So in this example we have seen how can we use the linearity property, time invariance and causality also. Okay. Next we'll see some problems from the book FFQ. So up to 5.10 we have solved it, I think long back. Now next we'll see the example 5.11. So the example 5.11 is the RC differentiator circuit, which is shown here. Which is shown here like this. R, C, this is E of t, okay, and this is my V0 of t. So suppose this circuit is given, so find the requirement for the RC time constant such that the output voltage V0 of t is approximately equal to the derivative of the excitation and approximately equal to proportionality constant. Okay, so that we have to show that what is the condition on the time constant such that this thing will be achieved. That is, output voltage will be approximately equal to k times the differentiation of V of t. So that we can solve by two ways. So if we will take what I am observing, that current through this is equal to current through R. Yes, is it not? So this I can write what is the current through the capacitor. It will be C d dt of the voltage between this. So it will be E of t minus V0. This is the current, and what is the current through R will be V0 R. So with this I can write V0 t is equal to RC into d dt of E minus V0. Okay, and in order to show that V0 should be equal to the d dt of Et, so what should happen? This V0 should be equal to 0, but this should not be the case. Okay, so in order to find out what should be the condition on RC, your V0 has to be much smaller than your excitation E. So with this condition I can write V0 of t will be approximately RC into d dt of E. Okay, and V0 is very small when R will be very small. So V0 tends to 0 means R tends to 0. So if R tends to 0, what does it mean? Time constant tends to 0. So this should be the condition. But here I am not revealing again more information from it. So suppose if I would like to go it into the Laplace domain. So let me see, can I extract some information from it? Okay, so the same circuit let me solve using the Laplace transform approach. So what will be V0 of S? V0 of S voltage across it will be this divided by this plus this. Okay, so it will be R divided by R plus 1 over CS into E of S, and which will be RCS upon RCS plus 1 into E of S. Okay, so what I can write, V0 of S will be equal to V0 of S will be equal to S into CR upon SCR plus 1. So this will be approximately, I can write SCR into E of S, so that I can write V0 of t will be approximately equal to RC into ddt of ET, right? And this will happen when your RCS plus 1 is equal to 1. It means that your RCS is much smaller than 1. Okay, and let me talk in terms of frequency domain. So S is sigma plus j omega, which is complex frequency, and if I'll substitute sigma is equal to 0, let me evaluate at omega. So this I can write as RC omega is less than 1. It means the frequency is very less than the inverse of your time constant. So what kind of information I observe that again? The frequency in this case, the circuit will act as a differentiator when your frequency will be very much less than the inverse of time constant, or the time constant will be much greater than the 1 by omega. Okay, so here you can see in Laplace domain at least I am able to say something. So it means some sort of information you will get it from time domain, some sort of information you will get it from frequency domain. So if you will use both, ultimately you will be able to extract much information from the system. Okay, next is 5.12. So the same approach, suppose I have this R and now C. Okay, and then this is my V0 of t, this is RC, and this is my E of t, right? And suppose this is the circuit is given, which is RC, and this is integrator. So the question is, find the requirement for the time constant such that the output voltage V0 of t is approximately the integral of the input voltage E of t dt. Okay, 0 negative to t. So that way you can find out, or you can find out the requirement on time constant. So to solve this, we will write V0 of S in terms of E of S. So V0 of S will be now 1 over Cs divided by R plus 1 over Cs into E of S, and if you solve it, this will be 1 over RCS plus 1, okay, into E of S. So V0 of S will be approximately 1 over S into CR into E of S. Okay, so in this, V0 of t will act as the integrator, right, of your and what is it, 1 over RC into E of t dt. And what is the condition? Condition is that RCS has to be much greater than 1. So it means that RC is greater than 1 over omega. It means that omega is much greater than 1 by RC. Okay, so this way you can show the requirement on time constant for this RC circuit. Okay, now next we'll take the example 5.13. So the circuit looks like 5.13, no? This is 5.13. So circuit is like this. There is a capacitor, resistor, and then inductor connected. So this is generalized source. Which source? It has not been given. This capacitor, 1/5 capacitor, resistor is 2 ohm, and inductor is 1 Henry, and you have to solve for I. So what is it? You have to find out the free response for I of t, and for the two conditions. One is when your source is voltage source, what is a particular source, it has not been given, and B is your current source. Okay, so in this what you have to find out? You have to find out the form only of free response R. Okay, so when I'll use the voltage source, how will it looks like? It will be, suppose the voltage source is this way. Let me draw it the circuit. Capacitor, then there is a resistor and connected with inductor here. Okay, so this is, let me call voltage source Vs of t. This 1/5 farad resistor and inductor is 1 Henry, and this is for current. I have to solve it. Okay, so if I draw the circuit like slate, what I have observed that, okay, voltage source is connected across the capacitor, so this capacitor is ineffective, right? Means how many independent initial conditions I have which I can set? Only one, that is initial current through the inductor. Means what? It consists of only one independent initial condition, that's why the order is 1 here. Okay, and this is the reason I am taking this example. So let me write the equation. So Vs of t will be equal to Ri plus L, simply di by dt, because capacitor is ineffective, and this I can write as 2I plus di by dt. Okay, and then what is the, if I would like to find out the free response, so free response means this has to be nullified, means it is 0. So what is for I? I will be, the root. So root will be P1 is equal to -2. So directly the free response you can write as, the form of free response when voltage source is connected like this is e raised to -2t into u of t. Okay, and this is the order 1, because it is the order 1 because there is only one independent initial condition is there, and that also you can see by writing the characteristic equation also. Okay, now next part is B. So if I'll connect the current source, now let us say what is the situation. So current source, capacitor is in parallel, then resistor and inductor connected to it. So this current source, let's say Is of t, this is 1/5 farad R, and this is L, and I have to find out the free response for I, right? So now what I am observing here, that I have a two independent initial conditions I can set. One is voltage across capacitor and current through the inductor, so there is no dependency. Okay, so I have two independent initial conditions, that's why order must have to be 2, and let us write the equation and solve it, as there is no contradiction I can observe here. Okay, so let us write the equation. So this will be Is, this is current to the capacitor, and this is my I. Okay, so Is will be Ic plus I. Ic will be C dV by dt, means it is 1/5 dV by dt plus I. Okay, which will be Is, and let me write for V. V will be your Ri plus L di by dt. Okay, and this will be what V will be di by dt plus 2I. Okay, so what will be my Is? I'll substitute V of t in this case, so di by dt plus 2I plus here I. Okay, so now if I solve, it will be 1/5 of d2I upon dt square plus 2/5 of di by dt plus 1/5 of I. And if I would like to solve for the free response, means what? Your Is has to be 0. Okay, so if Is has to be 0 and I want this coefficient to be 1, so what will be my resultant form? d2 dt square plus 2 di by dt plus 5I, which is equal to 0. So roots will be I1 and I2 here, or characteristic equation is p square plus 2p plus 5, or h square plus 2s plus 5, you want the way you can call. So it will be, I got is -1 plus -2j. Okay, and from that you can directly write the form I of t for the free response, which will be k into, it is e raised to minus complex conjugate, so it is e raised to minus alpha t into sine of omega t plus theta. So omega t is 2t plus theta. This is the standard form already we have seen. Thus, if the current source connected, I got the damped sinusoidal. Okay. So it is to be noted that the conclusion we can draw from it that the order of the circuit also depends on the energy source, which type of energy source you are using for the circuit. Okay. And also to be noted, while we are seeing this, if there would have been some initial energy or initial condition, either initial current through the inductor or initial voltage across it, you can shift it onto the right hand side and you can make it everything null, because the characteristic equation is not at all depending on the initial condition, it is independent on initial condition. Okay. Next is 5.14. So this is say I have voltage source here, then there are 2 points to this one source again connected, there capacitor, then inductor, and then in series with the inductor resistor connected. And suppose this battery is of 4 volt. Okay, previously it was connected at port 1, now it moved to point 2, and this is my E of t. Okay, and capacitor is of 6 farad, this is 2 Henry, 4 ohm. So I find I of t, and given that when your E of t is e raised to minus t sine 2t. Okay, so with that I think Laplace transform is the best way to solve such kind of circuit. Okay, so I'll write, if I'll move the switch from position 1 to position 2 at t is equal to 0, what I can write, E of t is equal to, again as this is in parallel with source, so this is ineffective, so I can write 2i to di by dt plus 4i. Okay, and I'll take the Fourier Laplace, and what is E of t, e raised to minus t sine 2t, which will be 2 di dt plus 4i, and suppose initial conditions are 0 here, so what is the Laplace, take it the Laplace on both side, so it will be 2 over s plus 2 square plus 4, and on the right side it will be 2s I of s plus 4 I of s, and from that I can write for I of s as 1 over s plus 2 into s square plus 2s plus 5. Okay, now from that I'll get it the complex conjugate root here. Okay, so the roots are minus this roots s1 2 are minus 1 plus minus 2j. So now I can use the partial fraction, so it will be k1 over s plus 2 plus k2 s plus 1 plus 2j plus k2 complex conjugate of s plus 1 minus 2j, and I can evaluate for k1 and k2. So k1 you can multiply s plus 2 with this at s is equal to minus 2, so k1 I got it 1/5. Then similarly for k2 at s plus 1 plus 2j multiplied with this 1 over s plus 2 into s plus 1 plus j into s plus 1 minus 2j, it is 2j, and that evaluating at s minus 2j. So if you will substitute everything, this will vanish, so it comes out to be r into e raised to j, it is a 1 by 10 into e raised to minus j, tan inverse of it is 1 by 2 coming. Okay, and now we have already know that you can write it in the short form directly into the form as 1/5 of e raised to minus t plus e raised to minus t into sine of 2t plus theta, that is tan inverse of 1 by 2 into u of t. Okay, so that way you can solve. There may be the multiplier const here and there, you can check it out. The next example is 5.15, and the problem is like this. For the circuit given as this R, this is L, okay, and this is E of t, R, L, and you have to solve for I of t. That this, let me read out the problem. Switch is closed at t is equal to 0. Yeah, we have closed it, and solve for I of t when initial conditions are 0. Okay, and voltage source is E of t, which is equal to sine omega t plus theta into E of, means if switch is closed, ultimately it is sine omega t plus theta into E of t. Okay, so the question is, what should be theta in terms of R, L, and omega, so that the coefficient of free response is 0. Okay, so for first part we have to solve for I of t. Now already we have solved it, so let me directly write I of t, the form which we obtained in the last classes. K into e raised to minus r by lt plus Vm, it was r square plus omega square into sine of omega t minus tan inverse of omega L by r. That was the form. Okay, and this was for Vm sine omega t. Okay, when your excitation was x of t, or whatever the excitation, it was Vm sine omega. And now here what is it? It is sine omega t plus theta. So Vm is 1. So now I of t I can write as k into e raised to minus r by lt plus 1 over square root of r square plus omega square sine of omega t plus theta minus tan inverse of omega L by r. Okay, and now what I have to do, this first part is over. Second part I have to find out such that the coefficient of free response is 0. Okay, so coefficient of free response is 0 means if I am asking free response, I of 0 will be 0, so it will be 0, which is equal to k into e raised to minus r by lt, that is 0. So I am evaluating it, t is equal to 0, so which is 0 equal to k plus 1 over r square plus omega square sine of theta minus tan inverse of omega L by r. Okay, and from here I can write k is equal to minus 1 over r square plus omega square sine of theta minus tan inverse of omega L by r. And what has to be done? Free response, the coefficient of free response has to be 0. So k will be 0 when theta will be equal to tan inverse of omega L by r. Got it? So theta has been expressed in terms of omega L and r. Okay, now next is 5.17. We'll skip 5.16 because it is again the same. 5.17 is like this. R, C and L are in parallel form. To this I of t is given, and this is 1/4 ohm, 1 farad is capacitor, and this is 1/3 Henry is inductor. Okay, and I have to solve for voltage V of t, let's say. Okay, and I of t is given as 4 into e raised to minus 2t into u of t. So you have to find out what is my V of t. Okay, so to calculate, first let us take it the Laplace of I of t, which is 4 upon s plus 2, and I know this current will be this plus this plus this. Okay, so I of t will be this current is V of t by 1 by 4 plus C into this dV by dt plus 1 over L integral 0 negative to t V of tau d tau. Directly apply the Laplace. So it is 4 over S plus 2. It is 4 into V of S plus C is S V of S. Assume the initial conditions are 0 plus 1 over S means it is L is 1 by 3, so 3 by S into V of S. So this I can write as 4S plus S square plus 3 over S into V of S. So now this V of S will be 4S upon S plus 2 and S square plus 4S plus 3, and then I will find out the roots. So 4S upon S plus 2, what are the roots? Minus B, minus 4, 16, and these are the real roots, so it will be S plus 1 and S plus 3. This is easy to solve, so simple roots, so I will solve. K2 S plus 2 and K3 S plus 3, you know how to find out the residues. So K1 is minus 2, K2 is 8, which is at S plus 2, okay, and K3 is minus 6. So my V of t will be minus 2 e raised to minus t plus 8 e raised to minus 2t minus 6 e raised to minus 3t. Okay, this is 5.17. 5.18 is based on the complete response. Already we've seen that. 5.17 already we have solved. This is what 5.17, 5.18 based on the complete response, and 5.19 in the last class we have solved that. Okay, so this way we can solve the circuit using the differential approach or the Laplace transform approach. Okay, if you analyze the circuit using differential approach, you will get it some information. Again, if you analyze using Laplace transform, you will get it the different sort of information. So if you use both the approaches, at least you will be able to extract much detailed information from the circuit. Okay, so today we stop here. Thank you very much.